Hello, dear friends. This is the part of our vibration course. Um, uh, in our vibration course, we discuss about the free vibration of a simple pendulum or a free vibration test. So, in free vibration, we can model free vibration with the help of simple spring mass model. So the spring is attached to a rigid support, and the mass is fixed at the end of the spring. And then the initial excitation is given to the mass in the form of either displacement or velocity. So this is a simple illustrative example for the analysis of simple harmonic motion or single degree of freedom motion of a free vibration case. So the vibration is called free vibration, that it has given only an initial excitation. And then it is called undamped vibration because the damping property of all aspects are neglected from this system. And there is no viscous damping also attached to the system from the oscillating system. It is only consisting of spring and mass only. This is the mass and this is the spring. So the spring will deform and restore back without losing any energy. So it is simply moving sinusoidally without stopping. So it is called a free vibration. So it is free because there is no force, no external force applied on it. If there is some external force on it, we call it a forced vibration. And it is undamped free vibration due to neglected damping system. Even the damping of the material property, the damping from the environment, like air frictions, these all are disregarded from this system. And this is an ideal system for the vibration analysis. Okay, so this is a free damping or simple harmonic motion of spring, a simple spring mass system. Okay, so let's see what we are going to see on that. This is the case of free vibration and undamped free vibration case. Here we have only consider, for example, here the spring and the mass and dashpot are the elements of vibration. From this, k is equal to, for example, this is some example, not exact. K is equals to 10 Newton per meter, M is equals to 1 kilogram, and the C, which is the damping value, which is 0 Newton second per meter. So for this case, there is no damping. That's why we call it as undamped. Okay, so the system starts to vibrate from the maximum position here and goes to the lowest peak point and come back to the same peak. All the peak points are in the same amplitude, down in the same, up in the same, so that there is no energy loss, there is no motion decay here. It is simply oscillating. Okay, as we see from here, it is oscillating in the same manner, up and down. It reaches to the maximum lowest position, comes back to the up position, so that the system will not decay or stop the motion. So this is the velocity in meter, and this is displacement in the meter, and this is dy dt, that is velocity in the meter per second. So we can observe from these two graphs, there is a phase difference that occurs. Okay, here it starts from this point, but in this case it starts from somewhere here. This implies that there is a pi/2 or 90-degree phase difference. So this is a sine wave. We can see this is a sine wave. The velocity is represented with sine wave, and this is cosine wave. Okay, and so they have a phase difference. Okay, so cosine graph and sine graph we can observe here. In the case of sine graph, the mean position is 0 here, but here the mean position is in somewhere, and it oscillates like constantly like this. So this is a simple harmonic motion case, undamped for undamped vibration analysis. Okay, so this is all about undamped free vibration illustration. Let's see some damped vibration case. Actually, in damped vibration case, we have 3 different cases based on the damping factor or the damping value. For example, if the damping value is very small, or zeta value, which is damping coefficient zeta, which is equals to less than 0, no, less than 1, that implies that the system can vibrate, but will decay with kind of exponentially. Okay. When the zeta value equal to 1, that implies critical damping case. Then the vibration will go go down very fast in the first cycle without crossing the mean position. It will go to far distance in time. And when the zeta value is greater than 1, that is called overdamped case, then it will also, the first vibration or the first motion goes down and then immediately stops at some point in the time. So let's see, this is underdamped case. This is obviously underdamped case because here we can see K10, K is equals to 10, that is spring constant, mass 1, and the C is equal to 0.5. This 0.5 means actually it is not depend on C, but it depends on the zeta value, the dimensionless quantity zeta. That will be how we can calculate zeta is the part of the lecture. So we can see it on that point, but when zeta is less than 1, that is underdamped case, and the system will vibrate like this. Finally, it will decay at some point of time. So the decay here is known as a logarithmic decay. If we draw some graph from here to there, we can plot a beautiful decaying curve. From bottom also the same thing happen. So then this decay is called a logarithmic decay, which is equivalent with the maximum amplitude x in the case of simple harmonic motion, the maximum amplitude x times e to the power of minus zeta omega nt. So zeta is the damping constant, omega nt is the natural frequency of the system, and time is t. So with that factor, it will decline. Okay. Okay. So there is also a logarithmic decline from in every cycle. For example, from here to here, it is we have one cycle here, the second cycle, third cycle. So in every cycle, there will be a constant, not a logarithmic decline of amplitude occur. That is x2. If I consider this as x1, this as x2, so x2 over x1, which is calculated. So that is the part of actually the lecture. In the case of damped vibration case, we will see those points. And this lecture I will post on the same lecture there. Okay, so here also the same thing. Amplitude of this one is the displacement and velocity are in phase difference also here. Okay, so this is also another case. The second case, in the case of damped vibration, that is when it is critically damped. When it is critically damped, that zeta value is equals to 1. So that we can calculate and find. So during that time, the amplitude of this motion immediately goes down within the first cycle and goes in the form of asymptotic approach to the time axis. Okay, so this is the critically damped case. When it is over damped case, what will happen? This graph is not giving such graph. Anyways, let's see. This graph immediately comes down and will stop somewhere around here. It will not continue like this. Maybe this is an extension of critically damped vibration case. Okay, so this is what we call the 3 cases of damped vibration. And this graph illustrates the amplification factor or amplification ratio versus frequency ratio graph. Okay, so in 3 different cases, for zeta value less than 1, that means for underdamped case, how it behaves, the graph behaves. If the zeta value goes to 0, then this amplification ratio to frequency ratio goes to infinity. It goes to infinity for 0 or no damping case. That means that also may be a special case of resonance. And when zeta value is very small, that means 0.1 is very small, still the graph like this. This implies still there may occur a resonance on those points. But when zeta is 0.2, we can see this graph. Okay, for zeta 0.3, we can see this graph, zeta 0.5. Okay, and then zeta is equals to 1, means critically damped. Okay, so for the critically damped case, it comes like this. So this graph is for the critically damped and underdamped case, and also for no damped, that case of simple harmonic motion case. Okay, so that frequency ratio, that the frequency of the system over the frequency of natural frequency ratio is here. And here also you can see the phase angle versus the frequency ratio. So for the same case, okay, for critically damped case, you can see this graph. This is for critically damped case. Okay, so here for the frequency ratio equal to 1, it is vertical here like this. For frequency ratio less than 1, here we can see the graph like this for zeta is equals to 0 case, especially no damping case. You see, this is no damping case, and this is critically damped case. As we increase a small damping, the graph goes like this. Again, this graph also goes like this, and this is the graph for zeta value 0.5. Okay, so these are important floats in the analysis of damped overdamped, no, critically damped, no damped, and underdamped case. So this is a kind of square wave generation by harmonics. Okay, this is initially it was harmonic vibration. From that, the square waves are produced. Okay, so this is some frequency spectrum square waves. Another the Laplace transform case. The Laplace transform case, as we know, the input function is excitation. Okay, we'll provide some excitation, which is in terms of amplitude, frequency, or phase, and the system will resonate, or that the system will respond. That the system consists of mass, damping, and stiffness, and then the output is the vibration amplitude, or the vibration frequency, or the vibration phase. That is, x of omega is the output, f of omega is the input, and the system contains this h of w. Okay, so this is the frequency response model of so on that we can see for some mass 1 kg, K 1.93, zeta 0.1, we can see this distribution for the magnification factor x over f and the frequency in hertz. Again, here there is newtons of the this is frequency spectrum, actually the square waves. Okay. The one which we have seen in the previous slide is this one. Okay, and then frequency spectrum resulting vibration. This is a frequency spectrum vibration. And let's see some other case like this transverse vibration, torsional vibration, and other case in the case of beams. Okay, this is multi-degree of freedom system, which is 2 degree actually. So look, this is a vibration of cantilever beam. The beam is fixed here and vibrating about. This is lateral vibration. The lateral vibration of cantilever beam. Okay, so here we can see kind of one mood shape. Okay, the second one is the torsional vibration, which is twisting about its axis. So that is another mood shape of cantilever I-beam. Okay, let's continue. There is also another vibration. This is the vertical bending. Okay, when we give a vertical excitation force on the end of free end of the beam, then the beam will vibrate like this. Okay, and this is with various mood shapes actually. And this second lateral bending. Okay, actually, this is the first lateral bending. We can see here a simple bending case, but if we see here, there is a second mood shape. There is a second mood shape in the beam. So this is what we call lateral bending in second mode. Actually, when we are analyzing vibration, we'll find the eigenvalues. The eigenvalues, lambda 1 and lambda 2. So the system will vibrate for lambda 1 and various omega, the natural frequency, omega 1 and omega 2, if we consider 2 degrees of freedom. So in the case of 2 degrees of freedom, omega 1 may be the first mode of vibration. That is the first simplest the first frequency. Then omega 2 is another second frequency in which the system will vibrate and second mood shape. Okay, so that is the case. So this is also second torsion. We have this first torsion. Okay, this is the first torsion, the first mode of vibration we call. But when we come to here, this is the second, we can see second mode. Okay, mood difference is there. So in vibration analysis, knowing the natural frequencies, various natural frequency of the system is the one of important thing. And then identifying the mood shapes of vibration is also another important case. Okay. So this is second mode of vertical vibration. For example, this is the first case that it is vertically deflecting up and down with a normal kind of vibration. But if we see this, it vibrates in the second mood shape. Okay, that means maybe for the second lambda value. Actually, this is in 211 hertz frequency. But how about this one? Let me check for the first case. This is in 93.65 hertz. Sorry, this is 39.7 hertz. The lowest natural frequency, 39.7, or we can take it frequency hertz. But let's go to this case. It is 211 hertz. Okay, let's see the. I have to start from the very beginning in order to identify. For this right and left, that is called lateral vibration in the first mode. It is vibrating 15.368 hertz. Okay, just take these notes, 15.36 hertz. But okay, when we come to this, it is vibrating with 93.653 hertz. This is the second lateral bending. Okay, I'm talking for the lateral bending case. Okay, now this is torsional. The first torsional, 24.876 hertz is the vibration mode for the torsional, the smallest torsional vibration frequency. Let's see the next torsional vibration mode. This is second torsion. Second torsion is vibrating with 114.725 hertz. Okay, yeah, it is like. So this is all about vibration. Okay, so thank you very much for watching this video. It will give you some highlight on the course of vibration. So just follow my vibration videos, which I'm uploading to my YouTube site. It maybe helps you. Okay, I'm just simply doing my best, and watching is for you, for your benefit only. Okay, so thank you very much.